Hi guys, John the Quant here. This is week 6 of the Data Science Bootcamp that I'm presenting to you guys on YouTube for free, and I'm also guiding at the Community College of Aurora. Now this week is all about fitting a good model. Last week we learned all about the different kinds of models, and this week we're learning how to fit a good one. Now, this is step 3 of that process, and it's all about cross-validation and hyperparameter tuning. If you did not start with step 1, which is fitting a baseline, I highly recommend that you start there, and that's going to pop up over here. All right, so once we know what hyperparameters are from step 2, now we need to choose the best hyperparameters to get the best performance out of our model. So let's see how to do that. Last step in fitting a good model is tuning those hyperparameters. So model tuning means finding the hyperparameters that are going to give us the best performing model. Okay, in general, the only way to find the best hyperparameters is to try like a whole bunch of combinations and measure the performance of each combo. So the most important thing to remember when tuning a model is that we care about out-of-sample performance, not in-sample performance. So out-of-sample performance is how well the model does on data it hasn't seen before. New data that we probably don't even have real answers to. Okay, this is how well models do in production, so this is what we care about the most. In sample performance, this is how well the model does on data that it has seen before, the training data. And in most situations, most models perform very well on in-sample data, but that doesn't always translate to good out-of-sample performance. And we've already been tracking out-of-sample performance by splitting our data into training sets and testing sets, and the model has never seen the test data, so the model's performance on the test data should be similar to the model's performance in production. But wait! As soon as we measure the model's performance on the test set, it doesn't really count as out-of-sample data anymore. So if we keep testing models on the same data, we're actually in danger of overfitting the model to the test set. But we also need a bunch of models for hyperparameter tuning. So we need a bunch of models that can't all see the same data. And we solve this problem using cross-validation. Okay, to perform cross-validation, what you're going to do is you're going to make a whole bunch of training sets and test sets, and that way you can use your data multiple times with less danger of overfitting your model. There are a number of ways to create a bunch of training and test sets, and we're going to look at 3 really common ones and talk about when you'd want to use each one. So the first one is called k-fold cross-validation. This is the most common one probably. And in this version of cross-validation, you randomly split your data into k different subsets. Here k equals 5. Okay, each about the same size. For example, if you have like 1,000 rows in your data set, then you split that data set into 3 groups of 333 rows each, or like 5 groups of 200 rows each, or like 10 groups of 100 rows each. Then you keep one of those as a test set and use the rest as a training set. Here, we're calling this a validation fold. This is a picture from Chaitanya Pula. Some research that this person did. It's just a very nice picture that really shows you how k-fold cross-validation works. All right, so for split 1, you're using the first fold as the test set or the validation fold, and using the rest of this for training. For the next one, using the second fold as a test set and the others for training. Then you're using the third fold as a test set and the others for training, and the fourth, and so on. And so we've created, even though we've got one data set here, we've actually made 5 different training and test sets. Next, we've got stratified k-fold cross-validation, and this is kind of the same idea as k-fold cross-validation, but it takes imbalance in the target variable into account. So if you have like a multi-class classification problem, and you're going to try to predict whether each row belongs to group 1 or group 2 or group 3, stratified k-fold cross-validation will make sure that each group has approximately the same proportion of rows in each fold. So, like if group 1 is 20% of all the rows, and group 2 is like 30% of all the rows, and group 3 is 50% of all the rows, then group 1 is going to be 20% in each fold, group 2 is going to be 30% in each fold, and group 3 will be 50% in each fold. This picture is from dataaspirant.com, and it's a nice picture that shows that, like, if this is your target class distribution, all right, about, I'm going to say 2/3 male and 1/3 female, not quite, but close enough, then when you stratify, it's doing the same thing as
k-fold cross-validation, but it's also ensuring that each fold has the same proportion of male and female observations in it. So if you have no imbalance, if you have a strong imbalance in your target, then you want to use stratified k-fold cross-validation. If you don't have much of an imbalance, you can just use regular k-fold. Scikit-learn automatically stratifies, I believe. Now, the last one we're going to talk about is called Monte Carlo cross-validation. For those of you that don't know a lot about geography, Monte Carlo is part of Monaco, and Monaco is a city-state on the Mediterranean Sea, and it's surrounded by France, and it's known for being rich. But the Monte Carlo part of the city is really known for gambling. So go ahead and watch James Bond GoldenEye or like Iron Man 2 to learn more. Okay, in statistics, when we say Monte Carlo, we typically mean simulating a random process. Here, Monte Carlo means we're going to create a bunch of training and test splits by randomly picking rows of data. And this is similar to bootstrapping, but we typically don't sample with replacement in Monte Carlo cross-validation, and we always sample with replacement when bootstrapping. If we sample with replacement, then bootstrapping, we can think of Monte Carlo cross-validation as bootstrapping a bunch of training and test sets. So in bootstrapping, a single row can be chosen more than once. And in Monte Carlo cross-validation, a single row is usually only chosen a single time, although we can allow rows to be chosen more than once. So here, I made this visualization. All right, so this is our original test, our original training set. And then using Monte Carlo cross-validation, we've randomly chosen a test set here 3 different times. And the important thing that you can see, you see this dot here? This was the test set in fold 1, and it's in the test set in fold 2. In the other two, in k-fold and stratified k-fold, there was no overlap. An observation could only be in one test set. Whereas in the Monte Carlo style, an observation can be in the test set multiple times. So Monte Carlo cross-validation, it's a lot less structured, and there are some problems with that. But it also allows you to create a larger number of training and test splits, a larger number of cross-validation folds than k-fold cross-validation does. All right, now that we've talked about cross-validation, we can actually tune hyperparameters. Okay, scikit-learn makes cross-validation easy. There are implementations for all 3 of the cross-validation schemes and like a whole bunch more cross-validation schemes in scikit-learn. And it makes tuning hyperparameters even easier. We don't have to do the cross-validation ourselves at all. Scikit-learn has objects created specifically to use cross-validation to run experiments and tune hyperparameters. It is really easy, and we're going to look at 2 options. First, we're going to start by creating a base model. Okay, a dummy classifier. We're using the transformed diabetes data here, and we're using a dummy classifier to make a stratified, a proportional random baseline. And I have fit that to the training data already. Then I'm going to look at the accuracy of the baseline. I've got accuracy score, classification report, confusion matrix, and the confusion matrix display. So the baseline model is accurate 52% of the time. Its recall is 62 and 33, neither of which is very appealing. And then as you can see here, what we want from a confusion matrix is for most of the observations to be on this diagonal, and for the opposite diagonal to be pretty much even. So even though these 2 are even, there are way too many observations off the diagonal for this to be a very good model. All right, the first cross-validation scheme we're going to use is called grid search. So when you have a group of hyperparameters and you want to test all of the combinations of specific values, you're going to use a grid search. This tuning method is going to go through every combination of hyperparameters that you give it, and it's going to track the model's performance with each combination. Now, the good thing about using a grid search is that every combination gets tried, so you know that you are getting the best set of hyperparameters. But the downside to that is that the number of combinations can grow really big, really fast, and it's going to be super slow for all but the simplest tuning experiments. So let's go ahead and try one. So here we're going to use a support vector classifier, and then from scikit-learn.model selection, we're importing grid search CV. Let's pull that up, grid search CV real quick, and have a look at the documentation to see how it works. Okay, so this it takes in an estimator, which is any model. It takes in a parameter grid, and you can tell it what function to use for scoring and some other things. How many cross validations to do. Let's see what it does by itself. If I can scroll down, here we go. All right, so CV default is none. If none, then it uses 5-fold cross validation, and it uses stratified as well. Okay, if Y is binary, then it uses stratified k-fold cross validation. So this is going to do automatically by itself. It's going to do 5-fold stratified cross validation for us. All right, so here our parameters that we're going to try. We're going to try all the different kernels: RBF, poly, linear, and sigmoid. Then we're going to try gamma is either going to be auto or scale or 0.5, and then C we're going to do 0.1, 0.5, 1, and 2. Now this is 1, 2, 3, 4, okay, and then there are 3 values for gamma, and there's 4 for C. So we have 4 times 3, which is 12 times 4, or 48 different possible combinations. And a grid search is going to try every combination. So it is going to try all 48, and there are also 5 folds. So down here it tells us fitting 5 folds for each of 48 candidates, totaling 240 fits. So this is going to fit 240 different models and try to figure out which model is the best one. Which of the 48 candidates is the best one. But it's fitting 240 models, so you can understand how this can get really big really fast. So in order to do it, we first create the model, which is the SVC, and then to the grid search, you have to feed in the model, which is SVC. You have to feed in a parameter grid, which should look like this. It's a dictionary with the different parameters in it and different values. And then verbose, I set equal to 3 because I wanted to show me all this. You don't have to let it show you anything. And then refit equals true. So refit, as it tells us over here, it says refit an estimator using the best parameters on the whole data set. So whenever this is done, and it's tried everything, and it finds the best parameters, it is going to make a new model on the entire data set. And then we just fit it here. You can see how it goes through 5 cross-validation folds. Okay, so this is the first one. C is 0.1. Gamma is auto. Kernel is RBF. Okay, the first combination. And here's the score for each fold. And it tells you how long it took too, and it's taken 0 seconds because this is fitting really, really fast. And it just does that for all of them. Let's look at this one. This is the 5 folds for C equals 0.5, gamma equals scale, and kernel equals linear. And so on. It fits 240 different models. And then it returns this thing at the end there. So I'm looking at the best score, and then I'm pulling out the best estimator so we can see how it actually does. So its best score, it said, was 76.2% accuracy. That's the best out of anything. And the one that did the best had C equals 0.5, gamma equals auto, and kernel equals sigmoid, which is kind of interesting because I would not have guessed those. And now let's see how well it did. Remember, our baseline was 52% accurate, so we're already doing a lot better there. And it was also had a recall of, what was it? I believe it was 60-something and 30-something? 62 and 33. Whereas this one has 85 and 61. So this is a lot better in terms of recall than the baseline. And then our confusion matrix display. Again, we want most of the observations to be on the diagonal, and we see that they are. And then we want everything off of the diagonal to be pretty well symmetrically distributed, which it kind of is. So this definitely looks like a much better model than the baseline. And we found our best hyperparameters, again, using the grid search. The next thing we're going to try is called a random search. So what do we do if we have too many hyperparameters for a grid search? We saw before we were only tuning 3 hyperparameters. We ended up with 48 combinations, which means we had to fit 240 different models. Okay, so what do you do if there's just too many? Well, you test a random set of combinations. Okay, and that's what the scikit-learn randomized search CV does. You give it a list of values for hyperparameters, and it tries random combinations. You can also give it distributions for the hyperparameters using the SciPy package, and it'll draw random samples from that distribution, which is really cool. So let's try it now. From scikit-learn.model selection, I'm importing randomized search CV. And from scipy.stats, I'm importing uniform. And this is a uniform distribution from SciPy. So, like, say, down here, I know that gamma should be between 0 and 10, but I have no idea where it should be between 0 and 10. It can be anywhere between 0 and 10. So that's what this means. Uniform between 0 and 10. All right, gamma can be anything, any number at all between 0 and 10. C also can be any number at all between 0 and 10. I don't know where it should be. I just know it should be somewhere between 0 and 10. So here, we're trying all 4 kernels again. Then we've got uniform gamma between 0 and 10, uniform C between 0 and 10. Shrinking is true or false, and class weight is none or balanced. So this honestly could have infinitely many combinations, but if we pretend that it's the same and we had 3 and 4, this would be 4 times 3 is 12, times 4 is 48, times 2 is 96, times 2 again is 192. So this would be, and then if we were fitting 5 folds for each one, like in the grid search, that would be 192 times 5, or almost 1,000 models to tune these hyperparameters. So that's way too many. We're just going to test 25. So we're using the randomized search CV. We're giving it the model, support vector classifier right there, feeding it these parameters, which again can accept these probability distributions, which is really cool. And we're telling it just pick 25 random combinations and tell me everything about it. And when we use .fit, then it gives us the same information here. So this is 5 cross-validation folds for a model that has C equals 8.44. Our class weight is balanced. The gamma is 5.386. Kernel is RBF. Shrinking is true. And the score is not very good. Okay, and those fit really fast. Then if we go further down, here are some that took a little longer. This set here had C equals 7.23. It had the class weight as none. Gamma was 3.59. Kernel was poly. Shrinking was false this time. And the score, again, not that great. You can see that this time we had 25 candidates and 5 folds for only 125. So we actually fit fewer models here than we did with our grid search, even though we're tuning more hyperparameters than we did before. And it goes through all of that, and it tests everything, and then it returns one with C equals 9.39. That's really close to 10, which is interesting. Gamma is 2.16. Our kernel is linear, and shrinking is false. Then if we get the best score from that, it is 76.2. And again, going back up, look at that, 76.2. So we got, even though we got radically different hyperparameters, we got a very similar score for our best model. And then here, our recall is 88 and 59. Now that, our accuracy is also 78.15, which I believe is better. Yeah, 78 versus 76. And then 88 and 59 is also different from the recall, although not that different. Then if we look here at the confusion matrix display, we see that most of the observations are on the diagonal, which is what we want. But this off diagonal is actually less symmetrical than before, which is typically not great. But this is telling us that we're missing 21 people have diabetes that we missed, which is really not what we want. There's 21 people who are sick, and we're telling them that they're not sick, and that is bad. All right, one final note on hyperparameter tuning here, okay? So I want to mention two things that I don't think people talk about enough. Okay, the first one is that any decision that you make can be thought of as a hyperparameter. Okay, you can use similar techniques to decide like which scalar to use. All right, or what features to include, or like how many rows of data to train the model on, and more. You can use it to decide almost anything. But if you do too much tuning, it can inadvertently lead to overfitting. Even with cross-validation, you can still overfit if you just do too much exploration. And the number of combinations you can try before it becomes a form of overfitting, it depends on the amount of data you have. But a good general rule is to just make as many decisions as possible without running a cross-validation test, and then you tune the rest. The math has been done, and there is a formula for how many tests it is safe to use. I will see if I can find that paper, and if I can, I will post it below, so please have a look for that. Number two, there are more advanced hyperparameter tuning methods available. These are two of the simplest ones, and they are both offered by scikit-learn. But we also have something called Bayesian optimization. There we go. Yeesh. Bayesian optimization. It's not that hard to do on your own, but Bayesian hyperparameter tuning, it is similar to the random search method, but it uses the performance of previous combinations to try to pick a combination that will perform better. The randomized search just picks at random. The Bayesian search picks at random, but tries to pick better ones than last time. Okay, now cloud service providers like Amazon Web Services or Microsoft Azure or like Google Cloud Platform, they all have automated machine learning products that basically perform really complex hyperparameter tuning. If you see anything about AutoML, basically what that is doing is it's going to automatically create a whole bunch of features, automatically do some form of feature selection, and automatically do a really complex form of hyperparameter tuning and try to get you a good model just by trying everything. All right, let's go back to in person and wrap up.
And that was step 3 in our 3-step process for fitting a really good machine learning model. Now, in this week's mini project, you are going to be asked to create a baseline, and then you're going to be asked to explain a few hyperparameters, and then you are going to be asked to find the best hyperparameters for your model, probably using either the grid search cross-validation method or the randomized search CV method that we just saw in the video. Now, if you guys have any questions for me, please leave your questions in the comments below. If you scroll down and you see that other people have asked questions, I encourage you guys to talk to each other. All right, try to answer each other's questions or at least add to the conversation. You don't have to know everything in order to help other people learn, and that's what this is all about, is us learning together. So if you did learn something, please like this video, and if you want to keep learning with me, go ahead and subscribe. I'll see you later.